Men have always been fascinated by the sun, moon and stars. Even our remote cave-dwelling ancestors must have looked up into the sky and wondered at what they saw there. Were the sun and the moon gods, or at least the dwelling places of gods? Today, astronomy has become an exact science. It's the basis of all timekeeping navigation, and moreover, it is still one of the very few sciences in which the enthusiastic amateur can still make really important contributions. Many people believe that to take a real interest in astronomy, you need to spend a vast sum of money on a large telescope. I can assure you that this is not true. You don't need a big telescope, or even a telescope at all. There's a tremendous amount to be seen with the naked eye. The next step is, in my view, to use a pair of binoculars. They'll show you a great deal. But eventually, you may think about a telescope. And this is the first one I had when I was 10. That was in 1933. And this is how it works. The light from the object you're looking at goes through this glass lens known as an object glass. Actually, it's a compound lens, but no matter. The light rays are bunched up and brought to a focus, and the image is enlarged by a second lens known as an eyepiece. Note that it's the eyepiece which does all the magnification. The role of the object glass is to collect the light in the first place, and the bigger the object glass, the more light you can collect. This telescope has an object glass 3 inches across, and in my view, it's the minimum useful size. Rather than get a smaller telescope, go for binoculars. Now this is a different kind of telescope, a reflector. Here, the light passes down an open tube and hits a curved mirror. The mirror sends the light back up the tube onto a smaller, flat mirror. This sends the rays into the side of the tube when an image is formed and enlarged by an eyepiece as before. This telescope has a 6-inch mirror, and it's about the smallest, which is really useful. Inch for inch, a lens is more effective than a mirror. But today, we have vast telescopes. First, let's get the basic facts straight. The Earth on which we live is a planet, a globe over 4.5 thousand million years old and almost 8,000 miles in diameter. It moves at something like 66,000 mph around the Sun, which is a star. This may surprise some people. The Sun is a perfectly ordinary star, and it appears so much larger and hotter than the other stars only because it's so much closer to us. The distance between the Earth and the Sun is approximately 93 million miles. Now that may sound a long way, and by normal standards it is, but it isn't far to an astronomer. In astronomy, we have to get used to immense distances and vast spans of time. Nobody can really appreciate them. I certainly can't, but we just have to accept them. The stars are so far away that they look like points of light, and we can't see them in the daytime simply because the sky is too bright. To show you how far away they are, let me give you a scale model. We will represent the Earth-Sun distance by 1 inch. So where must we put the nearest star? Over 4 miles away. No wonder that the stars look so much feebler than the Sun, even though some of them are much more powerful. The Earth isn't the only planet. There are 8 others, all moving around the Sun at different distances and in different periods. The Sun's family, or solar system, is divided into 2 well-marked parts. First we have 4 small, solid planets: Mercury, Venus, the Earth and Mars. Then comes a wide gap, in which move thousands of dwarf worlds which we call minor planets or asteroids. Then come 4 giant planets, Jupiter, Saturn, Uranus and Neptune, and one odd little world, Pluto, which doesn't fit into the general scheme and may not really be a proper planet at all. The planets look like stars with the naked eye, and some of them are brilliant, but they have no light of their own, and shine only because they're reflecting the rays of the sun. This is also true of the moon, which really does go around the Earth and is much the closest natural body in the sky. We have only one moon, but other planets have more. Saturn has as many as 18. The stars aren't really fixed in space, but they don't seem to move much over periods of many lifetimes compared with each other. Not so with the planets, which are much closer to us. They seem to shift slowly against a starry background from one night to another, and this is how the ancients first realized that they were different from stars. The rule is the further, the slower, and the stars are so far away that, relative to each other, they hardly seem to move at all. Of course, the whole sky moves round from east to west, but this is only because the Earth is spinning on its axis from west to east. We are observing from a moving platform, so to speak. The Earth spins on its axis in roughly 24 hours. Northward, the axis points to the north pole of the sky, marked fairly closely by a brightish star, the pole star. This means that the pole star hardly moves at all, and everything else turns around it. If you take a camera at night, point upwards at the pole star, and give a time exposure, you will get this effect. As the stars move, they leave their trails. If you go to the North Pole, you'll see the pole star vertically overhead. Go south of the equator, and you won't see the pole star at all, because it will stay below the horizon, and there isn't a bright south polar star. Just as the sun is king of day, so the moon is queen of night. And the moon really is near. Its mean distance from us is less than 250,000 miles. Fly 10 times round the Earth, and you will cover a distance greater than that between the Earth and the moon. It takes just over 27 days to complete one circuit, and of course it shows phases or apparent changes of shape from new to full. When it's almost between the sun and the Earth, its dark or night side is turned towards us, and we can't see the moon at all. This is the true new moon. As it moves along, we start to see a little of the day side. The moon becomes a crescent, then a half, and then, when it's on the far side of the Earth with respect to the sun, full. After that, the phases are repeated in reverse order, and we have the next new moon. When the full moon passes into the shadow cast by the Earth, its supply of direct sunlight is cut off, and we have an eclipse of the moon. The moon doesn't, usually, vanish completely, because some of the sun's rays are bent onto it by way of the shell of atmosphere surrounding the Earth. But the moon turns a dim, often coppery colour, until it passes out of the shadow again. Eclipses don't happen every month, because the moon's orbit is tilted, and on most occasions it escapes eclipse. I've said that the moon is much smaller than the Earth, and it has less mass. If you could put the Earth in one pan of a gigantic pair of scales, you'd need 81 moons to balance it. This means that the moon doesn't pull so strongly as the Earth. Its gravity is weaker, and this has one very important effect. The moon has no air. The air which we're breathing on Earth is made up of untold millions of tiny particles of air, all flying around at high speeds. If a particle could travel outward at 7 miles per second, it would escape the pull of our gravity. Fortunately, our air particles can't travel as fast as that. But on the moon, escape velocity is only 1.5 miles per second, and that's not enough to hold the air around the moon. Any air the moon may once have had has long since leaked away into space. Today, there's no atmosphere there, and therefore no water and no life. All the surface details are sharp and clear-cut. No mist, no cloud, no rain, no weather. Even with the naked eye, we can see details on the moon. Broad, dark plains, which we still miscall seas, even though there's never been any water in them. We still use romantic names. The Sea of Serenity, the Ocean of Storms, the Bay of Rainbows, and so on, because it was once believed that they were true seas. There are high mountains, often named after Earth mountains, but the whole lunar scene is dominated by the craters, which are everywhere. Some of them are well over 100 miles across. You can see these with any telescope or good binoculars. But the appearance changes very markedly from night to night. Remember, the moon shines only by reflected sunlight. When the sun's rays are coming straight down and there are almost no shadows at all, it may be difficult to identify the craters. So full moon is the very worst time to start looking at it through a telescope. The Earth spins round once in 24 hours, but the moon takes just over 27 days. If you're on the moon, a lunar day is almost as long as 2 Earth weeks. And the moon's rotation period is exactly the same length as the time taken for the moon to go once round the Earth. This means that the moon keeps the same face turned towards us all the time, and there's part of the moon that we can never see from Earth. The idea of travel to the moon is very old, but of course no ordinary flying machine can take us there. An aircraft can't work unless there's air around it, and there's no air between the Earth and the moon. Our atmosphere doesn't extend upward for more than a few hundreds of miles, and the moon is almost 250,000 miles away. The only answer is to use a rocket, which works by what Isaac Newton called the principle of reaction. Every action has an equal and opposite reaction. Consider a firework rocket. It's made up of a hollow tube filled with gunpowder. When you light the blue touch paper and retard immediately, the powder starts to burn. It gives off hot gas. This gas rushes out of the rocket's exhaust, and as it does so, it kicks the rocket in the opposite direction. The first unmanned rockets to reach the moon were Russian. They were sent up in 1959, and one of them went right around the moon, sending back pictures of the far side, which we can never see from the Earth. As we expected, the far side proved to be just as crater-scarred and just as barren as the side we've always known. In 1969, the first men went to the moon. The spacecraft Apollo 11 carried 3 men: Neil Armstrong, Buzz Aldrin, and Michael Collins.
Eagle, you're looking great. That's 40 feet down, 2.5. Picking up some dust. Houston, Tranquility Base here. The Eagle has landed. I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
They found a strange place. Aldrin described the scene as magnificent desolation. There was no sign of life, either past or present. The moon has always been sterile. On the moon, a man has only 1/6 as much weight as he does at home, so everything seems to happen in slow motion. Other missions followed, the last one in 1972. By now, we have a good knowledge of the moon. It's about the same age as the Earth, around 4.5 thousand million years, and most astronomers believe that the craters were produced long ago when the moon was hit by solid bodies from space, but almost nothing happens there now. Yet before long, we should be able to set up a proper lunar base. This must certainly happen during the 21st century, and I'm very ready to believe that some of you, now watching this video, will be able to go there. Meanwhile, do take a telescope or binoculars and look at the moon's mountains, craters, and waterless seas. But I think it's time to start our journey, and where better than the Sun, the centre of our solar system. One thing you must not do is to look directly at the Sun through any telescope or binoculars. It isn't even safe to stare at it directly with the naked eye. It's very hot indeed. Even the surface temperature is not far short of 6,000 degrees centigrade, and it's also very large. Its diameter is 865,000 miles. That's more than 100 times greater than that of the Earth. And you can pack 1 million globes, the volume of the Earth, inside the Sun and still leave room to spare. If you focus the Sun's light and heat onto your eye, you will blind yourself permanently. The trap is that some small telescopes are sold with dark sun caps, and it's said that it's safe to put the sun cap over the eyepiece and then look direct. Believe me, it isn't. No dark cap can give proper protection. It's always apt to shatter without warning, and a second's exposure will be tragic. There's only one rule for looking straight at the Sun: don't. However, there is one way. Point the telescope at the Sun without putting your eye anywhere near the eyepiece, and project the Sun's image onto a screen held or fastened behind the eye end. You will see the Sun's disk well, and you may see dark patches known as sunspots. These spots aren't really black. They look dark only because they are around 2,000 degrees cooler than the surrounding surface. You can't always see them. Every 11 years or so, the magnetic activity which causes spots on the Sun is very active, and there may be many groups of spots. At other times, as in the mid-1990s, the Sun is quieter, and there may be many spotless days. The Sun takes several weeks to spin on its axis, and so if you plot the spots from day to day, you will see them being carried across the Sun's face. It's always worth doing, and of course you could do that in the daytime. We say that the Sun is burning, but it isn't burning in the same way as a coal fire. The Sun shines because of what we call nuclear transformations going on inside it, near the centre of the globe, where the temperature is at least 14 million degrees, probably rather more, and the pressure is colossal. Over 70% of the Sun is made up of hydrogen. Near the core, strange things are happening. The bits of hydrogen are running together to build up bits of a heavier gas called helium. And each time this happens, a little energy is set free, and a little mass, or weight if you like, is lost. It's this energy that keeps the Sun shining, and the mass loss amounts to 4 million tons per second. Imagine the weight of 4 million coal trucks. But please don't be alarmed. The Sun is so huge that it won't change much for several thousands of millions of years yet. Most of what we know about the Sun had been learnt by using instruments based on the principle of the spectroscope. What we usually call white light isn't really white at all. It's made up of a combination of all the colours of the rainbow, from the red to orange, yellow, green and blue to violet. If you pass a beam of sunlight through a glass prism, you will split it up into a coloured band. Crossing this band are dark lines. Each dark line is due to one particular substance, and so we can tell what the Sun's made of. When the Earth, the Moon and the Sun are exactly lined up, the Moon will block the Sun out for a few minutes, causing what we call a total solar eclipse. The Moon is a small world, only just over 2,000 miles across, so it's much smaller than the Earth. Its diameter is only 1/400th that of the Sun, but it's 400 times nearer, and by sheer luck, the two bodies appear the same size in the sky, or nearly so. When this happens, we can see the Sun's outer atmosphere, and the sight is magnificent. Round the Sun's edge can often be seen masses of red hydrogen, which we call prominences. And beyond these comes the glorious pearly corona, which spreads out in all directions. If you have the chance to see a total eclipse, don't miss it. The problem is that the Moon's shadow is only just long enough to reach the Earth, so that you have to be in just the right place at just the right time. We always know when eclipses are going to happen. The last total eclipse visible in England was in 1927. The next will be on the 11th of August, 1999. Using spectroscopic equipment, we can now see the prominences at any time, and we can take films of their motions. They can shift very rapidly indeed. But this does need special equipment, and again I say, be careful. I don't apologize for stressing this, because it is so important. You have only one pair of eyes. Of course, the Sun is the ruler of the solar system. So let's remind ourselves of his family and take brief looks at them one by one. 4 small planets, Mercury to Mars. A wide gap filled by the midget asteroids, and then the 4 giants. We come first to Mercury, which many people have probably never seen. It's small, only 3,000 miles across, closer in size to the Moon than the Earth, and quite a long way away. On average, it's a mere 36 million miles from the Sun, and it speeds round in a mere 88 days. The problem is that it's always in the same part of the sky as the Sun, so with the naked eye, you can see it only when it's at its best, either low in the west after sunset, or low in the east before dawn. Look for it by all means, but don't sweep around with binoculars unless the Sun is completely below the horizon. You might look at the Sun by mistake. Because Mercury is closer to the Sun than we are, it shows phases similar to those of the Moon, and for much the same reason, bearing in mind that Mercury goes round the Sun, not round the Earth. When full, it's on the far side of the Sun, so it won't be visible. Very occasionally, when new, it may pass in front of the Sun and show up as a black spot. This is called a transit. The next time this happens will be in 1999. Because Mercury is small and lightweight, it has very little atmosphere. One spacecraft has passed by it, Mariner 10, in 1973 and 1974, and sent back pictures showing a rocky, cratered landscape, very like that of the Moon. Of course, it's hot. The surface temperature rises to hundreds of degrees, but the nights are bitter, and the nights on Mercury are very long because the planet is a slow spinner. I can't imagine that anyone will go there in the foreseeable future. If they could, they'd find a barren, scorching landscape under a black sky. Still, it's worth looking for Mercury just for the fun of finding it, and yearly almanacs will tell you when and where to look. Planet number 2, Venus, is as different from Mercury as it could possibly be, and you can't mistake it, because it is so very brilliant. Like Mercury, it shows up in the west after sunset, or the east before sunrise. It looks almost like a small lamp, and it can even cast shadows. This is partly because it's bigger than Mercury, almost exactly the same size as the Earth, and partly because it's nearer. At its closest, it's only about 100 times as far away as the Moon, And of course, it shows phases from new to full. It doesn't often pass in transit across the Sun's face. It last did so in 1882, and it won't do so again till 2004. So there can be nobody now living who's ever seen a transit of Venus. But though Venus and the Earth are near twins, they are non-identical twins. Look at Venus through a telescope, and all you'll see will be the top of a layer of cloud. But you can't see through those clouds. There's no such thing as a clear day on Venus, and the atmosphere is different from ours. It's made up chiefly of the heavy gas carbon dioxide, and those shining clouds are rich in sulfuric acid. Add the fact that the surface temperature is nearly 1,000 degrees Fahrenheit, and the pressure is at least 90 times that of our air at sea level, and you'll realize that Venus is not a very pleasant place. The Russians have landed automatic probes there and sent back pictures of the surface, but our best maps have been made by using radar-carrying spacecraft, of which the latest was Magellan. Magellan has shown us huge volcanoes, which may well be active. We'll even go for a simulated ride over Venus. Look at this towering peak. And I'm quite sure that nobody will go there in our time. Venus is odd in many ways. It spins very slowly the wrong way. So from Venus, the Sun rises in the west and sets in the east 118 Earth days later, giving a full rotation period of 243 days. This is longer than Venus's old year of nearly 225 Earth days. All in all, the differences seem to stem from the fact that Venus is over 20 million miles closer to the Sun than we are. It may have had seas once, but they've long since evaporated. We come next to Mars, the red planet. It really is red, which is why it was named after the god of war. It is smaller than the Earth, but larger than the Moon. It takes 687 Earth days to go around the Sun, and its own day is just over half an hour longer than ours. Telescopes show a red disk with white ice caps at the poles, and dark markings which were once thought to be seas, but are now known to be areas where the red, dusty stuff had been blown away by winds in the thin Martian atmosphere, exposing the darker surface below. Years ago, astronomers believed they could see streaks on Mars which were taken to be canals built by the Martians, whatever they might be, in a vast irrigation system. But, alas, the canals don't exist. They were simply tricks of the eye. Spacecraft have flown past Mars and sent back pictures showing craters, plains, valleys, and huge volcanoes, one of which, Olympus Mons, is 3 times the height of our Everest and is crowned by a 40-mile crater. In the 1970s, Viking spacecraft made controlled landings there, mainly to search for any signs of life. They didn't find any, and it now seems that there's no living thing on Mars, mainly perhaps because the atmosphere is so thin and is made up of carbon dioxide. Using the Viking results, we can at least go on a trip over the Martian surface, and it's going to be spectacular by any standards. In the 21st century, I'm sure we'll set up manned bases there. But one thing we can never do is to go out into the open unprotected by space equipment. We can never turn Mars into a second Earth. Mars has 2 moons. They're called Phobos and Deimos. Both are very small. less than 30 miles across for Phobos, even less for Deimos, and they wouldn't be of much use in lighting up the dark Martian nights. Probably they are not genuine moons at all, but are asteroids captured from the swarm which lies beyond Mars. These asteroids are curious little worlds. We now believe that they are debris left over, so to speak, when the main planets were formed from a cloud of dust and gas surrounding the young sun. Next, the giants, beginning with Jupiter, which is almost 90,000 miles across, but it isn't solid and rocky. Use a telescope and you will see that it has a yellowish, flattened disk crossed by streaks which we call cloud belts. The surface is made up of gas, mainly hydrogen, and it's very cold. Deep inside the globe, there's almost certainly a hot core, surrounded by layers of liquid hydrogen beneath the clouds that we can see. Though Jupiter takes nearly 12 years to go once round the Sun, it spins on its axis in less than 10 hours, and this is why it's flattened. Centrifugal force makes the equator bulge out. Through any small telescope, Jupiter is a fine sight. You may even see the Great Red Spot, which is a whirling storm with a surface area greater than the Earth's. We've sent spacecraft to Jupiter, and the two Voyagers, which bypassed the planet in 1979, sent back superb views. They also told us that Jupiter is a dangerous world. It's surrounded by zones of deadly radiation, which would instantly kill any astronaut foolish enough to venture too close. There's also a very strong magnetic field, and the surface is in a state of constant turmoil with thunder and lightning. No, we'll never go to Jupiter. But Jupiter isn't alone. It has 4 large moons: Io, Europa, Ganymede, and Callisto. 3 of these are larger than our moon, and Ganymede's actually larger than the planet Mercury. You can see them with any small telescope, or even really good binoculars, and there's never any problem in finding Jupiter because it is so brilliant, brighter than any other star or planet apart from Venus. Of the satellites, Ganymede and Callisto are cratered and icy. Io has a red surface with active volcanoes. Since Io also moves inside Jupiter's lethal radiation zones, it must be just about the deadliest world in the entire solar system. Beyond Jupiter lies Saturn, second of the giant planets, smaller than Jupiter, but still much larger than the Earth. Its diameter is over 70,000 miles, over 9 times that of the Earth. Its makeup is not unlike Jupiter's, but is distinguished by its set of icy rings. To me, Saturn is the loveliest object in the sky, and when the rings are well placed, a small telescope shows them well. However, though they measure almost 170,000 miles from end to end, they are less than a mile thick, and when they lie edgewise onto us, and in 1995, they almost vanish. The rings look solid, but they aren't. Saturn's powerful gravity will quickly pull any solid or liquid ring to pieces. The rings are made up of tiny pieces of ice, all spinning round Saturn like tiny moons. In 1980 and 1981, the two Voyager spacecraft gave superb views of them. They are made up of many hundreds of ringlets and narrow divisions. All the giant planets have rings, but only Saturn's are bright. Saturn takes almost 30 years to go around the Sun at a mean distance of 886 million miles, so it takes a spacecraft a long time to get there. But there are also the satellites, at least 18 in all, but only one of them, Titan, is large. You can see it as a star-like point in a small telescope. The Voyager pictures show the top of a layer of orange smog. Titan has a thick atmosphere, but we couldn't breathe it, and the temperature is very low. There are two more giant planets beyond Saturn, Uranus and Neptune, and both have been passed by the same spacecraft, Voyager 2, which was launched from Cape Canaveral in 1977. By sheer luck, at the end of the 1970s, the four giant planets were strung out in a curved line so that Voyager 2 could pass by them one after the other. Jupiter in 1979, Saturn in 1981, Uranus in 1986, and finally Neptune in 1989, after which Voyager began a never-ending journey out of the solar system. It will never come back, and we're still in radio touch with it, though before long we'll lose contact and we'll never know what eventually happens to it. The outer giants are much smaller than Jupiter or Saturn, but still much larger than the Earth. They too have gaseous surfaces and darkish ring systems. Uranus is rather bland, but Voyager showed dark patches on Neptune, and Neptune's main satellite, Triton, proved to have poles covered with pink nitrogen snow. Triton is so cold that nitrogen, which is gaseous in our air, freezes out. You can just see Uranus with the naked eye, if you know where to look for it. But to see Neptune, you need a telescope. Finally, on the edge of the planetary system, there is Pluto, discovered in 1930 by my old friend Clyde Tombaugh. Pluto looks like a star in ordinary telescopes, but our best instruments can show that it has a companion, Charon. But Pluto's hardly worth ranking as a proper planet, because it is very small, smaller than the Moon. It has a very thin atmosphere and probably an icy surface. It's so far away that it takes 248 years to go around the Sun, but it has a strange path, and when closest in, it's actually nearer than Neptune. Not until 1999 will it again pass beyond Neptune's path. Unfortunately, though, no spacecraft have been anywhere near it. There seem to be large numbers of very small bodies in the far reaches of the solar system, but we also have to remember comets and meteorites. A comet isn't solid and rocky in the same way as a planet. A typical comet has an icy centre mixed in with rubble, never more than a few miles across. Most comets move around the Sun in long, narrow paths, some of them in periods of a few years, though others take so long that they come near us only once in many lifetimes, and we can't predict them. When a large comet nears the Sun, its ices start to boil off, and the comet's centre is surrounded by a head and often a tail or tails. As the comet moves outward again and cools, the head and the tail disappear, and tails always point more or less away from the Sun, so that an outward moving comet travels tail first. A comet is travelling far beyond the Earth's air, and it doesn't move perceptibly against the stars as seen with the naked eye. So if you see something moving quickly, it can't be a comet. It may be an artificial satellite, but if it's very quick, it'll almost certainly be a meteor. Meteors are so small and flimsy that they burn away harmlessly, but now and then the Earth is hit by a larger body, which may strike the ground intact and is then called a meteorite. Note that there's no connection between a meteorite and the shooting star meteor. Meteors are cometary debris, while meteorites almost certainly come from the asteroid belt. We know of many meteorite craters. There's a famous one in Arizona, almost a mile wide, formed when a meteorite hit the desert well over 20,000 years ago. There's always a chance of another major hit, and it could cause great damage. It's even been suggested that this did happen around 65 million years ago, and threw up so much debris that the climate was changed, and the dinosaurs, which had been lords of the world for so long, died out. This may or may not be true, but at least it's a possibility. And we've seen one major impact. In 1994, a comet was observed to hit Jupiter and destroy itself. Up to now, we've been talking about our own local part of the universe, but now it's time to look further afield, to the stars. This is a typical star field. And remember, every star is a sun, and our sun is an ordinary star. I've already said that the stars are very distant, so far away that it would be awkward to measure their distances in miles, just as it would be awkward to give the distance between London and Sydney in inches. Instead, we use a unit called the light year. Light doesn't travel instantaneously. It flashes along at 186,000 miles per second. So in a year, it covers almost 6 million miles, and this is what we call the light year. It takes 1¼ seconds for light to travel to us from the moon, 8.6 minutes from the sun, but over 4 years from the brightest star, Alpha Centauri, in the southern sky. I'm afraid it would take too long for me to give you a tour of the constellations, but believe me, it doesn't take long to learn your way around, because the patterns don't change. My method is to select a few prominent constellations and use these as guides to the rest. When I was a boy, I obtained an outline star map and made a pious resolve to identify one new constellation every clear night. Before long, I had a good working knowledge, and after all, there are only a few thousand stars visible with the naked eye. Of course, the constellation patterns are quite arbitrary, because the stars are at very different distances from us, and the stars in any particular constellation aren't really connected with each other. We are dealing simply with line of sight effects. So let's look now at the life story of a star. It begins by condensing out of a cloud of dust and gas. Gravity makes it shrink. It heats up inside and joins what we call the main sequence, unless it's too small in mass, when it simply shines feebly as a red dwarf before losing all its light and heat. Our sun-like star shines steadily for a long time, thousands of millions of years in the case of our sun, but when it starts to run short of hydrogen fuel, things happen. It starts to use different nuclear reactions, becoming a red giant. When this happens to the sun, the Earth will certainly be destroyed, I'm afraid, but as I said, this won't happen for around 4,000 million years yet. Next, the star throws off its outer layers and becomes what we call a planetary nebula. A bad name. It has nothing to do with a planet and is not a true nebula. The outer layers dissipate. What's left of the star shrinks to become a very small, very dense object called a white dwarf. All its atoms are crushed and broken so that you could pack a ton of white dwarf material into an egg cup. The best known white dwarf is the tiny companion of Sirius, which is as massive as the Sun, but only about 3 times the diameter of the Earth. After a very long period indeed, the star becomes a cold, dead globe. That's the story of a star such as our Sun. If the original star is much more massive, it will die more spectacularly. When it runs out of available hydrogen fuel, it collapses. There's an implosion, followed by a rebound, and the star literally blows itself to pieces in what we call a supernova outburst. This doesn't happen often, but in 1987, one of these explosions did happen in the southern system called the Large Cloud of Magellan, and became visible with the naked eye for a time. At its peak, it could match several thousands of millions of suns. And we're left with an expanding gas cloud, inside which is a tiny remnant even denser than a white dwarf. If the original star is more massive still, it can't even explode as a supernova. When the collapse starts, it's so violent and so catastrophic that nothing can stop it. The star shrinks and shrinks, becoming denser and denser, and pulling more and more strongly. Finally, it's pulling so strongly that not even light can escape from it. And if light can't do so, then nothing else can, because light is the fastest thing in the universe. The old star has surrounded itself with a forbidden area which can swallow up material, but from which nothing, absolutely nothing, can escape. It has become a black hole. Obviously, we can't see it, and we have to detect it by its effects on objects close to it which we can see. What happened to the old star, I'm afraid I can't tell you, because nobody knows. Unquestionably, black holes are the most bizarre objects in the entire universe. Our star system, or galaxy, contains around 100,000 million stars, of which our Sun is one. It's a flattened system, perhaps 100,000 light years across. The Sun, with its planets, lies almost in the main plane, nearly 30,000 light years from the center of the system. When we look along the main plane of the system, we see many stars in almost the same line of sight, and this produces the appearance of the Milky Way, that lovely band of radiance crossing the night sky. It's made up of stars. The stars look as if they almost touch each other, but this is an illusion. Actually, they're wide apart. We also know that the galaxy is rotating. It takes the Sun about 225 million years to go once round, a period sometimes called the cosmic year. One cosmic year ago, the most advanced creatures on Earth were amphibians. Even the dinosaurs lay in the future. I wonder what the Earth's going to be like one cosmic year hence. But if we could look at the galaxy from above or below, we see that it is a spiral, like a great Catherine wheel. This is no surprise either. Far away in space, we can see other spiral systems, although not all galaxies are spirals. What we do know for certain is that apart from a few comparatively nearby systems in what we call our local group, all the galaxies are receding from us and from each other. Edwin Hubble found that the further away a galaxy is, the faster it's racing away. The expansion is universal, and today we know of systems which are well over 10,000 million light years away and are racing off at over 90% of the speed of light. In fact, galaxies tend to occur in groups, and each group is receding from each other group. We are in no special position in the universe. You can see one problem here. If the rule of the further, the faster holds good, then eventually we will come to a distance at which an object is moving away at the full speed of light. We will then be unable to see it at all, and will have reached the edge of the observable universe, though not necessarily the boundary of the universe itself, if it has one. It seems that this critical distance is between 15,000 million and 20,000 million light years, but there is considerable uncertainty, and it may even be that there's a major error which may lead to a great deal of rethinking. Everybody wants to know how the universe began and how far it extends. At present, we can't answer either question. According to our present ideas, the universe came into existence at one particular moment in a Big Bang, around 15,000 million years ago, and has been expanding ever since. Whether the universe will finally contract and produce another Big Bang, again, we don't know. And to be candid, neither do we know why or how the Big Bang happened. We must go on trying to find out. So, all in all, there's a great deal that we still don't know, even though we found out so much in recent years. But to end, Let me say again that even if you don't want to save up for a powerful telescope, you can take a real interest in astronomy. Do some reading, get a star map, and learn your way around the night sky. Join an astronomical society, and you'll give yourself a lifelong hobby, as I have myself. I wish you all success and clear skies.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
That was President John F. Kennedy in 1961. I'm Patrick Moore. Throughout the years of the Apollo program, I had the privilege of presenting all the live coverage on British television. The video you're about to see will tell this history of the Apollo missions. I'm here in the Space Gallery at the Science Museum in London to tell the story. Here, undoubtedly, is one of the best space exhibitions outside the USA. And throughout this program, we'll take time to look at many of its fascinating exhibits. In 1961, Kennedy had spoken to the United States Congress. I believe this nation should commit itself, before this decade is out, to landing a man on the moon and returning him safely to the Earth. Bold words indeed. But it was the Soviet Union that had started the space age in October 1957 by launching Sputnik 1, the first of all artificial satellites. It was the Soviet Union who sent the first unmanned probes to the moon in 1959 and had obtained the first pictures of its far side. And it was the Soviet Union that had launched the first man to orbit the Earth, Yuri Gagarin. Yet Kennedy gave America less than 10 years to achieve the first moon flight.
Of landing a man on the moon and returning him safely to the Earth.
Apollo was born. Astronauts were selected. The original 7 included Alan Shepard, but not Neil Armstrong. The investigation of the moon went on. It was again the Russians who made the first automatic controlled landing, but American surveyors followed. And even more importantly, the orbiters flew round and round the moon and provided detailed pictures of the entire surface. Various bogies were disposed of. The moon was not covered with a treacherous layer of dust, as some astronomers believed. The great dark plains, still miscalled seas, even though there had been any water in them, were firm enough to bear the weight of a spacecraft. The moon had no air, but so far as could be ascertained, neither did it contain anything harmful. Its mountainous, cratered landscape awaited the arrival of man. America had some helpers. Werner von Braun who built the V-2 rockets at Peenemünde in the Baltic during the war, was in their team, and his expertise was unrivaled. If we look above where I'm standing, there's an example of his work, an actual V-2 rocket. The lunar project started to become international, though the Soviet Union was aloof and was planning its own moon landing, even though the Russians had to abandon it when it became painfully clear that their rockets were not sufficiently reliable. But American orbital satellites became more and more sophisticated. Space dockings, space maneuvers, all went well, more or less. More astronauts joined the program, including 3 named Neil Armstrong, Edwin, Buzz Aldrin, and Michael Collins. In orbit, or en route to the moon, there's no weight. Gravity is neutralized, but fears of excessive space sickness or loss of orientation proved to be groundless. So was the fear that spacecraft flying beyond the atmosphere might be battered by meteoroids. By 1967, everything was on schedule. Then, on January the 22nd, disaster struck. 3 Apollo astronauts, Grissom, White and Chaffee, were carrying out a ground test. They were inside an Apollo module when there was a sudden call of fire. Nothing could have saved the astronauts, America's first space martyrs, though sadly not the last. It says much for the planners and the resolve at NASA, America's space agency, that in less than 2 years, Apollo was once more on schedule.
S4B pre-press complete. Roger.
Flight booster. S1C pre-press complete. We're on in.
An Apollo mission is not so straightforward as might be thought. What you can't do is to take off, go to the moon, and come back in a single, uncomplicated vehicle. Takeoff is by rocket booster, and the power needed is immense.
Buses go, all engines.
Roger. Okay, Fido, how's it look?
Looks good here, flight. Good agreement.
Okay, booster, how do you look?
S1C looks good, flight.
Okay, Capcom, we go on the ground. Okay, we'll go at 1, Capcom.
The bottom part of the launcher falls away. Only the upper part continues on its way. The command module is the astronaut's space home. Once in lunar orbit, 2 of the 3-man crew enter the spidery lunar module and descend to the moon. When they're ready to leave, they use the lower stage of the lunar module as a launching pad.
Right away, Houston. Vector good. Ag shot. Good over. Roger, you have good thrust. Okay, 30 seconds. 308 your number.
They rejoin the 3rd crewman, the lunar module is jettisoned, and then homeward bound to splash down in the ocean. There is so much that can go wrong, and there's no provision for rescue if the astronauts make a faulty touchdown on the moon, or if the one ascent engine in the lunar module fails to work properly the first time. Tests went on. By October 1968, 11 years after Sputnik 1, Apollo 7 was ready to fly. It was not to go to the moon. It was to take astronauts Schirra, Eisel and Cunningham into a path round the Earth so that Apollo hardware could be tested. It worked well. Then, in December, came the first actual flight to the moon. Apollo 8, carrying astronauts Borman, Lovell and Anders, blasted away from Cape Canaveral to go around the moon. Never before had men been so far from the Earth. They were not to land, but they went into a path around the moon, and they were the first men to see the far side. It could be done. It was done. Apollo 9 was an Earth orbiter testing the Apollo equipment. And then, in May 1969, Apollo 10, carrying astronauts Stafford, Cernan and Young, again rounded the moon, sweeping low over the site where the next Apollo was to land. And here, at the Science Museum, we can see the actual Apollo 10 command module. From this craft, the astronauts orbited the moon and surveyed the site which had been selected for the first manned landing. That was to be the mission of Apollo 11. The site? The waterless Sea of Tranquility, one of the moon's great dark lava plains. That was where Neil Armstrong and Edwin Buzz Aldrin were due to land, leaving Michael Collins orbiting the moon in Columbia, the command module. But if Armstrong and Aldrin were to step onto the lunar surface, they'd have to be properly clad. On the moon, there's no air. And quite apart from the fact that you couldn't breathe, the lack of pressure around you would mean that you die in less than a minute. A spacesuit has to be pressurized, and it's bulky. But on the moon, you have only 1/6 of your Earth weight, which helps. Watched by television viewers all over the world, Apollo 11 took off. July the 16th, 1969. It reached the neighborhood of the moon in 3 days and went into orbit. Armstrong and Aldrin entered the lunar module, Eagle, and began the descent. Armstrong brought the Eagle down manually. It was a hazardous business. There could be no second chance. As they came in, their voices could be heard all over the Earth.
Eagle, we got you now. It's looking good, over.
Roger, copy.
Eagle, Houston, after yaw around, angled, S-band pitch, -9er, yaw, +18. Roger, you're a go to continue power descent. You're a go to continue power descent.
Altitude now 21,000 feet, still looking very good. Velocity down now to 1,200 feet per second.
You're looking great to us, Eagle.
Give us a reading on the 1202 program alarm.
Roger, we got you. We're going at alarm.
Good radar data. We're now in the approach phase. Everything looking good. Altitude 4,200.
Houston, you're a go for landing, over.
Roger, understand. Go for landing. 3,000 feet. Stop alarm. Altitude 1,600. 1,400 feet. Still looking very good. 700 feet, 21 down. 33 degrees. 100 feet down at 19. 1201.
1201. Roger, 1201 alarm. We're go. Same tide. We're go.
Altitude, velocity, light. 3.5 down. 20 feet. 13 forward. 11 forward, coming down nicely. 200 feet. 4.5 down. 5.5 down.
60 seconds.
Lights on. Six. Down 2.5. Forward. Forward. That's 40 feet down 2.5. Picking up some dust. 4 forward. 4 forward. Drifting to the right a little. That's okay. Contact light. Okay, engine stop.
We copy you down, Eagle.
Tranquility Base here. The Eagle has landed.
At 4 minutes to 4 in the morning, British summer time, on July the 21st, Armstrong finished his descent down the ladder.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Aldrin described the scene as magnificent desolation. Though it was daytime, the sky was jet black. On the airless moon, the sky is always black. Nothing moves. There's no wind, no weather, no sound. As Armstrong and Aldrin erected the American flag, they knew that it couldn't flutter. Walking around was interesting. With only 1/6 weight, everything happens in slow motion. But the astronauts had no time to waste. They had to set up a scientific station to be left behind so that they could go on sending back information. And they had to collect rocks to bring home for analysis. For over 2 hours, they stayed on the surface. Then they re-entered the lunar module and prepared for takeoff.
Houston, guidance recommendation is pings, and you're cleared for takeoff.
Only the top part of the Eagle would lift away. The bottom half, the launch pad, would remain on the moon.
Engine arm ascent.
All was well.
Beautiful. Very smooth. Very quiet ride. There's that one crater on there.
Eagle blasted off and carried Armstrong and Aldrin back to the command module.
1,000 feet high, 80 feet per second vertical rise. Eagle Houston, you're looking good at 2. Ping, zags, and missed all agree.
I'm going right down US 1.
Eagle Houston, going right down the track. Everything's great. Horizontal velocity approaching 2,500 feet per second. Roger. Some 120 miles to go until insertion.
They rejoined Collins, the Eagle was jettisoned, and the astronauts came home to splash down in the Pacific Ocean.
Some way, when those two Americans stepped on the moon, the people of this world were brought closer together. That it is that spirit, the spirit of Apollo, that America can now help to bring to our relations with other nations. The spirit of Apollo transcends geographical barriers and political differences. It can bring the people of the world together in peace.
The first men on the moon were back, but there was one delay. Though it was fairly sure that the moon was sterile, could anything harmful have been brought back? Just in case, the astronauts were put in strict quarantine until they'd been thoroughly examined. As expected, nothing was amiss, and quarantining was abandoned after one more mission. Next, Apollo 12 in November 1969, with astronauts Pete Conrad, Al Bean and Richard Gordon. This time, the launch wasn't so smooth. During takeoff, the Apollo was struck by lightning. Mercifully, it did no damage, but it was a nasty moment. This time, the target area was the Oceanus Procellarum, or Ocean of Storms, the largest of all the lunar seas. There was a special reason for this. Way back in 1967, the unmanned craft Surveyor 3 had landed there and was still sitting there. On the moon, there's nothing to disturb it. The Apollo 12 astronauts were scheduled to land so near Surveyor that they could walk over to it, cut bits off, and bring them home for analysis. Needless to say, this needed pinpoint navigation, but it was achieved. From the lander, Intrepid, Conrad and Bean did indeed go to Surveyor. The only hitch came when Bean accidentally turned the camera toward the sun and put it out of action, but otherwise all went well. Again, a scientific station was set up, known as ALSEP, Apollo Lunar Surface Experimental Package. There were experiments of all kinds, and all worked. Once again, the return journey was flawless. Surely nothing could go wrong next time. But it did. Apollo 13 was a near disaster. Trouble began early. The crew members chosen were James Lovell, Fred Hayes, and Thomas Mattingly. But at the last moment, it was found that all three had been exposed to German measles. Lovell and Hayes were immune, but Mattingly was not, and he was replaced at the last moment by Jack Swigert. The landing site was near the ruined crater Fra Muro in the Mare Nubium, or Sea of Clouds. It was to be made in the lunar module Aquarius. The code name for the command module was Odyssey.
Roger. Clock start, flight.
Roger. Start to go, all engines.
Roger. Okay, final, how's it look?
Looks good here, flight. Good agreement.
Okay, Booster, how do you look?
That's 1-3 looks good, flight.
Okay, Capcom, we go on the ground.
The launch was conventional. By now, many people were starting to become rather blasé.
Booster, how do you look?
We look good, flight. We'll go.
Okay, fired up.
We're go, flight. Looks good here.
Guidance, how's it look?
Good, flight.
Okay, Econ, GNC.
Looks good, flight.
Looks good, flight. Okay, Surgeon.
It looks fine. Through Max Q and we'll go, flight.
Roger, Booster. And go for staging, Capcom.
Confirming board out, flight.
Roger.
Staging, flight.
Roger.
Flight, final trajectory confirmed staging.
Roger.
Flight booster, then board out was way early.
Okay.
Flight confirmed. Number 5 engine down.
Roger. Booster, you don't see any problem with that, though, do you?
Negative, not right now, flight. All the other engines are go.
Odyssey had to be docked with Aquarius. This obviously was very much of a precision operation.
We're hard dock to Houston. Roger, understand hard dock. Good deal.
Okay, I can see the S4B now at the hatch window.
But when Apollo 13 was 178,000 miles from Earth, there was a sudden drama.
13, we've got one more item for you when you get a chance. We'd like you to stir up your cryo tanks. In addition, have Shaft and Trunnion
Okay.
for a look at the Comet Bennett if you need it.
Okay. Stand by.
Houston, we've had a problem here.
Flight guidance.
Go, guidance.
We've had a hardware restart. I don't know what it was.
Okay.
Houston, we've had a problem. We've had a main B bus undervolt.
You see an AC bus undervolt there, guidance? Or ecom?
Negative, flight.
Believe the crew reported it.
We got a main B undervolt.
We may have had an instrumentation problem, flight. Roger.
And we had a pretty large bang associated with the caution and warning there.
There'd been an explosion in the command module. The spacecraft had lost almost all its power. Part of the vehicle was blown out. It was a desperate situation. Brilliant improvisation, courage and skill saved the astronauts, though of course the lunar landing had to be abandoned. Using the engine of the lunar module Aquarius, the Apollo went round the moon and came home, though there were all sorts of emergencies.
Okay, let's get the cameras put away. Let's get all set to burn. We have one chance now.
It was a salutary reminder that space travel is risky. Had the explosion happened on the homeward journey, the astronauts would have been doomed. They would no longer have had Aquarius.
I'm good.
Okay, copy that. Farewell, Aquarius, and we thank you. Okay, LOS in a minute or a minute and a half. At entry attitude, we'd like Omni Charlie. And welcome home.
Thank you.
I recall, Captain, that when I spoke to you on the phone, you said that you regretted that you were unable to complete your mission. I hereby declare that this was a successful mission. From the start, the exploration of space has been hazardous adventure. The voyage of Apollo 13 dramatized its risks. The men of Apollo 13, by their poise and skill under the most intense kind of pressure, epitomized the character that accepts danger and surmounts it. Theirs is the spirit that built America.
But within a year, Apollo 14 was on its way, commanded by Alan Shepard, one of the original 7 astronauts, and incidentally, the only one of the original 7 who went to the moon. It was a personal triumph. Shepard had been taken off the active list because of ear trouble, but had insisted on an operation which had cured him. With him were astronauts Ed Mitchell and Stuart Rooser. Again, Fra Muro was the target, but this time there were no insuperable problems, and Shepard and Mitchell took with them a moon cart to carry their equipment. They walked further than any of the earlier explorers, though they became so tired they weren't able to go as far as they had hoped. There was one amusing incident. Before departing, Shepard drove the first golf ball on the moon. He claimed that it went miles and miles and miles. I wonder whether it will ever be found. Apollo 15 was dispatched in the following July. Astronauts David Scott and Jim Irwin were scheduled to land in the foothills of the lunar Apennines, near a deep, gaping crack known as the Hadley Rill. The third crew member, Al Worden, will carry out a series of experiments in the orbiting command module. There was a new departure. With them, Scott and Irwin took a moon car, powered electrically to allow them to drive across the moon. It seems a flimsy thing, but it was designed to operate only on the moon where the gravity is weak, and it proved to be a great success. Lunar dust was something of a problem. As David Scott told me, it got into everything, but at least it wasn't as deep as had been feared before the first unmanned spacecraft had landed. Again, ALSEP was deployed, and the view of Hadley Rill was indeed amazing. Two more Apollos remained. Apollo 16, in April 1972, landed in the lunar highlands. The walkers were John Young and Charles Duke, with Thomas Mattingly in the command module. By now, the scientific objectives were increasing, and more complex ALSEPs were set up. The scene was set for the grand finale with Apollo 17, which was launched the following December, 1972. Up to now, the astronauts had not been specialist geologists. They were very good at it, but the fact remained that no trained scientist had been to the moon, and this honor was reserved for Harrison Jack Schmidt, a professional geologist who was trained as an astronaut and added to the crew of the last Apollo. With him was a space veteran, Eugene Cernan, with Ron Evans in the command module.
We're right where we wanted to be for Station 2, and it looks like a great place.
The lunar module Challenger came down in the region of Taurus Littrow, near the edge of one of the lunar seas.
Big blocks. It looks like quite a bit of variety from here. Different colors, anyway.
Again, the moon car was brought into operation, and the astronauts drove around. Schmidt's expert knowledge proved to be invaluable. He could appreciate the nature of the rock and the soil, and nothing escaped him. Then, inside a small crater nicknamed Shorty, he found something very strange.
Oh, hey! There is orange soil. Well, don't move it till I see it. It's all over. Orange! Don't move it till I see it. I've stirred it up with my feet. Hey, it is! I can see it from here. It's orange.
Orange soil. What was it? Was it evidence of recent volcanic action? Alas, no. The color proved to be due to a very ancient glassy beads. But it was an exciting moment.
It's trench time. Jack, that is really orange.
The time had come to say farewell to the moon.
It's a rock composed of many fragments, of many sizes, and many shapes. When we return this rock, or some of the others like it, to Houston, we'd like to share a piece of this rock with so many of the countries throughout the world. We hope that this will be a symbol of what our feelings are, what the feelings of the Apollo program are, and a symbol of mankind that we can live in peace and harmony in the future. I'd like to just let what I believe history will record, that America's challenge of today has forged man's destiny of tomorrow.
Gene Cernan was the last to enter the lunar module, and the takeoff was recorded by the camera left behind on the lunar surface.
One, ignition. Right away, Houston. Vector good. Ag thought. Pitch over. Roger, you have good thrust. Okay, 30 seconds. 308 your number. Take coming through 1,500 feet, and H-dot looks good.
Apollo was over. So all in all, what did Apollo accomplish? There have been critics who have claimed that anything that men can do, machines can do better. This is simply not true. A computer can't think as well as the human mind, and without astronauts, our knowledge of the moon would still be inadequate. Not only of the moon itself, but of the Earth. Remember, the moon is an integral part of our own system. Moreover, the various experiments left on the moon have been invaluable. I need only mention the example, the solar wind collector, picking up particles sent out by the sun. Above all, perhaps, Apollo looked to the future. Since 1972, no one's been to the moon. There have been a few unmanned sample and return probes, and of course the American spacecraft Clementine, which explored the moon from lunar orbit in 1994 and sent back superb pictures. But the way ahead lies clear. Cost? Well, lunar missions are expensive, or so it seems, until they're compared with even a minor war. Reusable craft will certainly bring the costs down, and of course the first of these was the Space Shuttle. But not all of the shuttle's hardware is reusable. However, various other concepts are now being tested and will be totally reusable. So the initial outlay may be expensive, but if all goes according to plan, the cost must be dramatically reduced in the long term. With the collapse of the USSR, international collaboration in space has increased. In 1995, Russians on board the shuttle Atlantis changed places with an American on the space station Mir. And all this leads on to a lunar base, which must surely be set up within the next couple of decades. It'll be of immense benefit to mankind, and who knows where it, in turn, will lead. Wherever we look, we come back to Apollo. True, the basic impetus was political, but before the end of the program, it had turned into science. Without it, we would never have gone much further beyond the Earth. So, when we have our lunar base, and men and women are working there, never forget those immortal words by Neil Armstrong.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Hello, I'm Patrick Moore. Throughout the years of the Apollo space program, I had the privilege of presenting all the live coverage on British television. The story this video unfolds is truth, not fiction. The dramatic events which took place in April 1970 kept the world on tenterhooks for 9 days. I'm here in the Space Gallery of the Science Museum in London to tell the story. Here, undoubtedly, is one of the best space exhibitions outside America. And throughout this program, we'll take time to look at many of the fascinating details. But before I tell you about that near-fatal mission, I'd like to tell you how the Apollo program came into being. Our story begins on the 4th of October, 1957. On that day, Sputnik 1, the first artificial satellite, was launched by the Russians. Explorer 1, the first American satellite, followed 3 months later. Thus began the race for space between the two great nations. More than 100 years earlier, W.S. Gilbert had written, "They're going to send a wire to the moon, and they'll set the Thames on fire very soon." And in 1961, Yuri Gagarin became the first man in space. And 8 years later, the immortal words of Neil Armstrong, "That's one small step for man, one giant leap for mankind," rang out around the world. Inevitably, the moon had to be our first target. It's our faithful companion in space and stays together with us as we journey around the sun. Even a small telescope will show its mountainous, cratered surface with the broad, dark plains, which we still call seas, even though we know that there has never been any water in them. It's never much more than 250,000 miles away, and even the nearest of the planets, Venus, is always 100 times as remote. It was only in our own time that travel to the moon became a real possibility. Virtually all the journey has to be done in empty space, and only the rocket, which works by what Isaac Newton called the principle of reaction, will be able to do the job. It wasn't until 1926 that the first liquid-propellant rocket was launched. Only in 1957 that the Russians ushered in the space age by sending up the first artificial satellite, Sputnik 1. Yet, all in all, progress has been amazingly rapid. Less than 7 decades separated Orville Wright's first hop from Kitty Hawk to Neil Armstrong's step onto the bleak rocks of the lunar Sea of Tranquility. When President John F. Kennedy announced that the United States planned to send a man to the moon before 1970, he was very well aware of the problems ahead.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Space is a dangerous environment. It would be wrong to pretend that rockets are wholly reliable, and with also the moon itself to be considered. Would its surface be firm enough to support the weight of a spacecraft? There had been suggestions that the so-called seas, at least, might be covered with deep, treacherous dust layers. Much had to be done before a manned flight could be attempted, and the President's timetable was painfully short. Moreover, nobody really knew what the Russians were planning. One problem about the moon is its lack of atmosphere. It's smaller than the Earth, with a diameter of only a little over 2,000 miles, and it has only 1/81st of the Earth's mass. That's to say, if you could put the Earth in one pan of a gigantic pair of scales, you would need 81 moons to balance it. The moon's globe is also less dense than that of the Earth, and the escape velocity is lower, only 1.5 miles per second, as against our own 7 miles per second. This means that any atmosphere the moon may once have had has leaked away, and today the lunar world is airless. This also means it must be waterless and lifeless. It's a world of everlasting calm, and there can be no sound. Sound waves are carried by air. The lunar day is long. The moon spins round once in 27 Earth days, as against our own 24 hours. And the sky is jet black all the time. Yet, even before the Apollo program was conceived, much had been learned. And during the 1960s, the entire surface was mapped by automatic spacecraft, including the far side, which we can never see from Earth, because it's always turned away from us. As expected, the far side regions proved to be just as barren and just as crater-scarred as the hemisphere we've always known. More importantly, Russian lunar vehicles and American surveyors made controlled landings and showed no signs of sinking into dust. One obstacle at least was removed, and the Apollo plans went ahead with all possible speed. Inevitably, there were mishaps. The worst came in January 1967, not in outer space, but a mere 200 feet off the ground. During a routine test in an Apollo module, a disastrous fire caused the death of 3 astronauts, Grissom, White and Chaffee. Quite apart from the human tragedy, the accident caused a great deal of radical rethinking with regard to design and safety measures. It was remarkable, therefore, that the first crew-carrying Apollo was ready for launch less than 2 years later. On the 11th of October 1968, Apollo 7, carrying astronauts Schirra, Eisele and Cunningham, was put into a closed orbit round the Earth and remained aloft for over 10 days. Then, in the following December, Apollo 8 made the first circumlunar manned flight. The crew members were Borman, Lovell and Anders, and it was, of course, James Lovell who was later to command the ill-fated Apollo 13. The Apollo plan had to be complicated. It was simply too difficult to launch a spacecraft from Earth, land it directly on the moon, and bring it home. Of the 3 Apollo astronauts, 2 would make the actual descent in a lunar module, leaving the 3rd member orbiting the moon in the command module. At the end of the lunar part of the mission, the top part of the lunar module would blast back to rejoin the orbiting command module, leaving the bottom part of the lunar module on the moon's surface to act as a launch pad. After rendezvous, the lunar module would be jettisoned, would be either left in orbit or else deliberately crashed onto the moon. Therefore, the lunar module's role would be ended after rendezvous, and this proved to be of vital importance in the story of Apollo 13. Apollo 9 of March 1969 was another test in Earth's orbit. Then, in May, Apollo 10, carrying astronauts Stafford, Cernan and Young, made another circumlunar flight and did everything apart from the actual landing. And here, at the Science Museum, we can see the actual Apollo 10 command module. From this craft, the astronauts orbited the moon and surveyed the site which had been selected for the first manned landing, the waterless Sea of Tranquility, one of the moon's great lava plains. All went well, and the stage was set for Apollo 11. Apollo 11 was commanded by a civilian, Neil Armstrong, who had already been in space with the earlier Gemini program. So too had Edwin, Buzz Aldrin, who was scheduled to be the 2nd man on the moon. Note now that his name really is Buzz. He changed it from Edwin by deed poll. The 3rd crew member was Michael Collins. Though he didn't actually make the landing, he commented that at least he'd gone 90% of the way. Tension mounted as Armstrong and Aldrin began the descent. Although every possible precaution had been taken, it was still a jump into the unknown, and if the touchdown were faulty, there could be no possibility of rescue. The final landing was controlled manually by Armstrong, and then came his voice, loud and clear: "The Eagle has landed." Touchdown was 4 miles downrange of the plan point and a mere 37 seconds late. The date was July the 20th, 1969. It was natural that the astronauts should want to depart from their original schedule, which allowed for a period of sleep before starting the outside walk. With mission control approval, everything was put forward. At 4 minutes to 4 in the morning of July the 21st, which is summertime, Armstrong stepped off the ladder to be followed 20 minutes later by Aldrin. For the next 2 hours, 47 minutes, the surface activity went on. There were symbolic tasks, such as the setting up of the American flag, and also the deployment of scientific instruments. Above all, lunar samples had to be collected and stored. A television camera set up some 60 feet from the Eagle showed the entire scene, and the astronauts were seen clearly. Working under 1/6 normal gravity didn't prove difficult, and there were no mishaps. The next really tense moment came when Armstrong and Aldrin blasted back into orbit. The Eagle had only one ascent engine, and this had to work faultlessly first time. Mercifully, it did. The astronauts rejoined Collins in the command module, and the return journey was comparatively uneventful. Nobody could better Aldrin's description of the lunar scene as magnificent desolation. And here we can see a reconstruction of the Apollo 11 lunar module. This was originally planned for use in the James Bond film Diamonds Are Forever, but it was decided that an alternative method should be used to reproduce the visual effect. However, the model makers were persuaded to build it as planned, and it became part of the exhibition here at the Science Museum. Apollo 12 followed in November 1969. Astronauts Conrad and Bean came down within range of an old automatic surveyor probe which had been on the moon for some years and were able to bring parts of it home for analysis. For over 7 hours, they explored the region of the Oceanus Procellarum, Ocean of Storms, and once again, all went well. Like their predecessors, they were quarantined on return just in case they brought back any harmful substance. But thereafter, quarantining was abandoned since it had become clear that the moon was totally sterile. No life had ever existed there before it had been brought from Earth. So far, everything had gone with surprising smoothness, and all the manned Apollo missions had been, to all intents and purposes, trouble-free. But then, in April 1970, came Apollo 13. 13 is always said to be the unluckiest of numbers, and from the start, there were problems with the 13th Apollo. The selected crew members were James Lovell, Fred Hayes, and Thomas Mattingly. At the last moment, it was found that all three had been exposed to German measles. Lovell and Hayes were tested and found to be immune to the disease. Mattingly was not, and so he was replaced by Jack Swigert. It was not an auspicious beginning. Apollo 13 was scheduled to continue the work of the two earlier landings and to extend it. With each mission, the scientific content was increased. The target was the area of the ruined crater Fra Mauro in the waterless Mare Nubium, or Sea of Clouds, one of a group of 3 craters. There was nothing really special about the region, but at least it was another part of the moon. The landing was to be made in the lunar module Aquarius. The code name for the command module was Odyssey. During the launch, one of the motors cut off early, but otherwise all went according to plan, and Apollo 13 was on schedule as it went on its way moonward. It did so without the fanfare of publicity that had surrounded Apollos 11 and 12. So little had gone wrong with the NASA moon program since the earlier disastrous fire that it had come to be regarded as more or less routine, and people in general had become somewhat blasé about it.
This little tape recorder has been a big benefit to us in passing some of the time away on our transit out to the moon. And it's rather odd to see it floating like this in Odyssey while it's playing the theme from 2001. This is the crew of Apollo 13, wishing everybody there a nice evening, and we're just about ready to close out our inspection of Aquarius and get back for a pleasant evening in Odyssey. Good night.
Odyssey had to be docked with Aquarius. This obviously was very much of a precision operation.
We're hard docked, Houston.
Roger, understand hard dock. Good deal.
Okay, I can see the S4B now at the hatch window.
But then, when Apollo 13 was 178,000 miles from Earth, the whole situation changed, and changed dramatically. The drama was about to begin.
13, we've got one more item for you when you get a chance. We'd like it to stir up your cryo tanks. In addition, I have Shaft and Trunnion
Okay.
for a look at the Comet Bennett if you need it.
Okay. Stand by. Houston, we've had a problem here.
Flight guidance.
Go guidance.
We've had a hardware restart. I don't know what it was.
Okay.
Houston, we've had a problem. We've had a main B bus undervolt.
You see an AC bus undervolt there, guidance? Or ecom?
Negative, flight.
I believe the crew reported it. We got a main B undervolt.
We may have had an instrumentation problem, flight.
Roger.
And we had a pretty large bang associated with the caution and warning there.
The sensation I had, that I had felt a vibration accompanying the bang, not a large vibration or shudder.
Is there any kind of leads we can give them? Are we looking at instrumentation, or we got a real problem, or what?
We're reading 0 N2 pressure in fuel cell 1 and 13 psi on fuel cell 3 O2 pressure.
Okay, Barrett, what do you want to do? Open circuit fuel cell 1 and 3?
That's firm flight.
Shut down the reactance valve, and I asked for a reconfirmation, since when you do that, it's sort of irreversible. If you shut one of these things down, they only can be restarted from ground support equipment.
Yeah, that's because of AC. And it looks to me, looking out the hatch, that we are venting something. We are venting something out into space.
Okay, let's everybody think of the kind of things we'd be venting. GNC, you got anything that looks abnormal in your system?
Negative, flight.
How about you, Ecom? You see anything that, with the instrumentation you got, that could be venting?
That's a firm flight. Let me look at the system flight as far as the venting is concerned.
Okay, let's start scanning.
Here is a bulletin from ABC News. The Apollo 13 spacecraft has had a serious power supply malfunction that could cause the lunar landing mission to be terminated early.
I assume you've called in your backup ECOMs?
Flight, say again?
Have you called in your backup ECOMs now? See if we can get some more brain power in this
We
thing?
got one here.
Roger.
At the moment, the astronauts are continuing to try to isolate their trouble. A late report says the spacecraft now is operating on battery power alone. All unnecessary equipment is being turned off.
Okay, now let's everybody keep cool. We got the LEM still attached. The LEM spacecraft's good, so if we need to get back home, we got a LEM to do a good portion of it with. Okay, let's make sure that we don't do anything that's going to blow our CSM electrical power with the batteries, or that will cause us to lose the main or the fuel cell number 2. Okay, we want to keep the O2 and that kind of stuff working. We'd like to have RCS, but we got the command module system, so we're in good shape if we need to get home. Let's solve the problem, but let's not make it any worse by guessing.
My concern was increasing all the time. It went from, I wonder what this is going to do to the landing, to I wonder if we can get back home again.
Okay, I'm coming back to you.
Flight.
Go ahead.
I think the best thing we can do right now is start a power down.
Right about then, it was quite apparent to me that it was just a question of time that the command module was going to be dead.
You don't want to get fuel cell pumps off, do you?
We can do that on fuel cell number 1 flight.
Okay, well, let's make sure we don't blow the whole mission. The thing that concerns me is throwing equipment. We had a problem. We don't know the cause of the problem.
Flight, I've got a feeling we've lost 2 fuel cells. I hate to put it that way, but I don't know why we've lost them. It doesn't all tag up.
Network from Flight.
Flight network.
Bring me up another computer in the RTCC, will you?
We got one machine on the RTCC, and we got dual CPs downstairs.
Okay, I want another machine up in the RTCC, and I want a bunch of guys capable of running D-logs down there.
Roger that.
What all this means is only speculation at this point. First, though there has been some tumbling or rotation of the spacecraft, the astronauts do not appear to be in any immediate danger.
Tell you what, GNC, can you get somebody in the back room to try to figure out what the equivalent delta V is we're getting, so that we can see if we can backtrack to see if we can figure out what's venting? Roger, we'll give it a try, Flight. Okay?
When I looked up and saw both oxygen pressures, one absolutely 0 and the other one going down, it dawned on me, and I'm sure Jack and Fred about the same time, that we were indeed in serious trouble. The only way to survive the situation was to transfer to the LEM.
Flight Econ.
Go ahead, Econ.
The pressure in O2 tank 1 is all the way down to 297. We better think about getting in the LEM or using the LEM systems.
I'd say this is as serious a situation as we have ever had in manned spaceflight. We've always called the LEM a good lifeboat under those circumstances. If at any time in the mission, however, the LEM had separated and we had gotten ourselves into a rendezvous situation or the command module being around the moon, then what you state is absolutely true. It would be a fatal situation.
Almost 200,000 miles out in space, an oxygen tank had exploded, ripping off the side of the service module. The oxygen tank, situated here, well, you can see the damage. The Odyssey was disabled.
Tell them you from Flight. Go ahead, Flight. I want you to get some guys figuring out minimum power in the LEM to sustain life.
The astronauts rode in the lunar module attached to a lifeless command module. The scientific exploration mission had turned into one of survival. Apart from oxygen and the power saved for re-entry, the command module was dead. The guidance platform of Aquarius, designed to land and take off from the moon, would have to be used.
The first milestone was to get alignment on the LEM platform. Alignments are important, you know, because without knowing exactly which way the attitude of the spacecraft is in space, there's no way to tell how to burn or how to use the engines of that spacecraft to get the proper trajectory to come home.
The most important thing after survival was to align the LEM, or Lunar Excursion Module. In this situation, alignment is critical, because without knowing the direction of the craft, it's impossible to know how to use the engines to get the correct trajectory for Earth.
The position we are now on the Earth-Moon plane, we have to go around the moon to get back if we're going to use the DIPS engine. You would have had enough capability with the SBS engine, but of course we don't dare use that now. So we have to go to the back side of the moon and come back.
To get into the correct orbit around the moon, the crew had already departed from the trajectory that would automatically bring them back to Earth. They'd have to get back onto a safe course toward Earth. In order to do this, they'd have to round the moon on the far side and back.
He needs to put his throttle to min also, Flight.
Throttle to min?
Yes, he's at 29% now, roughly.
This maneuver, again, was completed on time, and because it was a manual burn, we had a three-man operation. Jack would take care of the time. He'd tell us when to light off the engine, when to stop it. Fred handled pitch maneuver, I handled the roll maneuver, and I pushed the buttons to start and stop the engines.
Aquarius, and you go for the burn.
%.
Okay, Aquarius, you're looking good.
First problem was solved, but there were many others. They were back on course for Earth, and they'd certainly have enough food and also enough oxygen to breathe, but drinking water was a problem. The astronauts had to ration themselves to 6 fluid ounces a day, and that meant severe dehydration. It certainly didn't help the condition of Fred Hayes, who had fallen ill and was causing great concern to everybody.
What we'll be doing till we get them back on the water is concentrating on everything that is their lives are dependent upon at the moment, rather than worrying about the accident, because there's nothing we can do about that now. It appears at the present time that everything is under control and that we have a safe situation at the moment.
Hey, I want to say you guys are doing real good work.
So are you guys, Jack.
We are about 70 hours from home, and we think we have the situation in control. We've projected the consumables as I've described, and we have a plan for carrying out the rest of the mission, but there's going to be no relaxation at all as far as that goes from now until splash.
Before the craft went behind the moon, a choice had to be made: where to bring them down. On their present course, they would have splashed down in the Indian Ocean. Recovery would have been difficult. A burn to bring them home faster would take them to the Pacific Ocean, very close to the recovery forces. There was a possibility of bringing them home even faster, which would seem the most logical thing to do in the circumstances, but they would then be placed in the South Atlantic, again away from the recovery forces. It was decided to bring them down in the Pacific.
We've run these simulators both here and at the Cape and at the contractors that continuously ever since last night. We've tried to simulate virtually everything that we've had the crew to do that is non-normal that they've done, and we've proven most everything that we've been able to run on the simulator prior to passing it up to them. There may be some details we haven't done, but at least we've checked the feasibility of everything we've done, and we'll continue to do that.
They passed 137 miles from the moon. For Lovell, it was the second time he'd seen the moon so close, but there was no time for contemplation. There was another critical burn coming.
Okay, look, let's get the cameras squared away. Let's get all set to burn. We have one chance now.
And in Houston, the newsmen prepared to tell the anxious world the astronaut's story. After Apollo 13 had separated from the Saturn third stage, the discarded hardware had been sent onto a trajectory toward the moon. Its impact was recorded by the seismometer left by the previous mission, Apollo 12.
By the way, Aquarius, we see the results now from 12's seismometer. Looks like your booster just hit the moon and it's rocking it a little bit. Over.
Well, at least something worked on this flight.
I'm sure glad we didn't have a limb impact, too.
Jim, you go for the burn. Go for the burn.
Roger, understand. Go for the burn.
Guidance okay?
We're good, flight. Control, okay? We're okay, flight. Tell me we're go, flight.
Inco okay?
We're good, flight. Ground confirms ignition.
We're burning 40%.
West Houston, you're looking good.
Roger. Shut down.
Roger, shut down. I say that was a good burn.
Roger, now we want to power down as soon as possible.
Understand.
After this, all but the life-sustaining systems were shut down.
I think the LEM spacecraft's in excellent shape, and I think it's fully capable of getting the crew back. I think, as we have found before, every time we've put the LEM spacecraft to a test, it's always done much more than it was guaranteed to do, and I think this is a good case in point.
The LEM water gun was leaking, and we shut that off. I guess it leaked about a quart of water, I would estimate. But it took me about 2 days to get my feet dry, and of course, I think you were all aware that the temperatures were going down in both vehicles, and it's made for very chilly feet for a couple days.
Lord, your astronauts will come back safe.
If I may be serious for one moment and ask the entire audience for a moment of prayer for the crewmen of the Apollo 13. We'll hold silence for a moment, please.
RCS-A stands at 62% and B at 62%.
I see we've gone a hell of a long time without any sleep. We're going to have to start thinking about getting people back to sleep again because I didn't get hardly any sleep last night at all.
Command module just slowly kept going down in temperature until I think just prior to reentry, it was down to about 38 degrees. And along with that, it was a sort of a chilling coldness. The walls were perspiring, the windows were completely wet, and it wasn't too healthy. I recall that we went in there to get some hot dogs one day, and it was like reaching into the freezer for the food.
If you want my opinion of how they handled the situation when it happened, they handled it exactly like we'd expect them to. They were about as well on top of it as anybody could be who knew what we knew, which isn't very much, I'll have to admit. But I think they did everything right within the knowledge that was available to us in a timely fashion, which is what all we expect of them. I think they did a beautiful job of it.
The astronauts faced a further problem, their own exhaled breath. The lithium hydroxide, the chemical used to take carbon dioxide out of the air, was not sufficient in the lunar module. They'd have to adapt the canisters from the command module to fit the hoses in the LEM. The ground control improvised an adapter to solve the situation out of the materials they knew the astronauts had available on board. Cardboard from a checklist, plastic bags, and tape. It's amazing to think that with all this sophisticated technology involved in Apollo missions, that one of the major problems could have been solved with these.
At this point in time, I think the partial pressure of carbon dioxide was reading about 15 millimeters. And we constructed two of these things and put them online, and I think within an hour, the partial pressure of CO2 was down to 2/10.
So you see that survival now became one of initiative and ingenuity, and it was one which the ground continually helped us along. We had all kinds of people on the ground trying to think of ways of extending our lifetime.
There was yet another burn. It was to make a mid-course correction to get Apollo 13 into the narrow corridor through the atmosphere for a safe return to Earth.
We're at burn attitude, flight.
Knowledge.
Ignition. Thrust looks good. Shut down.
Hang in there, it won't be long.
There were moments when I didn't know how much consumables we had, whether we could make it back or not, but in a situation like that, there's only one thing you can do. You just keep going, and you just keep thinking up where you can get more consumables. And so that's exactly what we did.
On April the 17th, they prepared for re-entry. After a small course correction burn, they jettisoned the damaged service module.
SF,
Copy that.
and there's one whole side of that spacecraft missing.
Is that right?
The whole panel is blown out, almost from the base to the engine.
It's really a mess. Man, that's unbelievable.
Next, they got back into Odyssey to jettison Aquarius prior to entry into the atmosphere.
Okay, copy that. Farewell, Aquarius, and we thank you. Okay, LOS in a minute or a minute and a half. At entry attitude, we'd like Omni Charlie. And welcome home.
Thank you.
Odyssey Houston standing by, over.
Okay, go over.
Odyssey Houston, we show you on the mains. It really looks great.
Apollo 13.
Apollo 13, this is recovery. We observed your RCS burn, over. The recovery, Apollo 13 is descending. Apollo 13 is recovery, over. Photo 1 spliced in the system.
At 12:07 Houston time on April the 17th, the command module Odyssey splashed down in the Pacific. If there had been relatively little publicity when Apollo 13 blasted away from Cape Canaveral, there was certainly no lack of it now. Strangely, for a few days, while the astronauts were in deadly danger, every nation seemed to become united, and there can have been no country in which no prayers were said for their safe return. But in what shape were they? All three were suffering from woolly-headedness and disorientation, and all had lost weight. In Lovell's case, as much as 14 pounds. In addition, Fred Hayes was suffering from infection and fever. But all recovered in a surprisingly short time, and a week later they faced the press at a major conference. Some of Lovell's words were particularly worth remembering. "I'm very much disappointed, just as Fred is and Jack is, that we couldn't complete the mission. We certainly wanted to make a lunar landing. Frau Murer has so much to offer, we thought. But this was my 4th space flight, and there are many people in our organization who have not flown and who deserve to fly and are talented enough to fly. And they deserve a mission. If the NASA team feel this team should go back to Frau Murer, I'm certainly willing to go there. But otherwise, I think other people ought to do it."
I recall, Captain, that when I
A typically unselfish comment. And as we now know, none of the Apollo 13 astronauts did go back to the moon.
I hereby declare that this was a successful mission. From the start, the exploration of space has been hazardous adventure. The voyage of Apollo 13 dramatized its risks. The men of Apollo 13, by their poise and skill under the most intense kind of pressure, epitomized the character that accepts danger and surmounts it. Theirs is the spirit that built America. Your mission served your country. It served to remind us all of our proud heritage of a nation, to remind us that in this age of technicians and scientific marvels, that the individual still counts, that in a crisis, the character of a man or of men will make the difference.
Apollo 14, launched on January the 31st, 1971, was commanded by Alan Shepard, who, less than a decade earlier, had been the first American in space. 3 more Apollos followed, and the program ended in December 1972 with number 17. And all in all, what was learnt from Apollo 13? The purely scientific results were naturally meager. Some images of the far side of the moon, that really was all. But in other ways, the experience was invaluable, simply because it showed what could be achieved by a combination of courage, skill, and improvisation. But there's one aspect of the drama which is immensely sobering. The astronauts were saved because they were able to use the engine of the lunar module Aquarius. But had the explosion happened on the return flight instead of the outward journey, there would have been no Aquarius. It would have been jettisoned, and the astronauts would have been helpless. In the whole of man's first ventures to the moon, no mission will have a more honored place than this one. It was indeed a story of tragedy turned into triumph. And the world will never forget Lovell, Hayes, and Swigert, the heroes of Apollo 13.